Welcome to a lesson with Dr. Powell. Let's take a look at left hand and right hand limits. Namely, if we have a function, and maybe there's a jump in it, but it's still a function, it still passes the vertical line test. It's only defined in one place here. Now, suppose that this y value up here is 5, and this y value down here is 3. And this function is f, the whole function in the whole picture here. Now, if we were to think about what would make this function continuous just to the right of this x value, suppose this x value is 1. So maybe we're interested to know from 1 onward, so starting at 1 and going this way, what, as we take our x values getting close to 1, what's the y value that would ensure that this function would be continuous from 1 to infinity? Meaning that I don't jump up and go up here. Now apparently the hole is right here. That's what I fill in, right? Now, if this were filled in, and I just ignored what was up there, so I kind of took that point away right there, and I made it fill in down here, then this would be, f of x would be continuous at x equals 1, but only on the right side. On the right side. So you could call that right continuity, if you will. And you also can think of it this way. The limit as x approaches 1 on the right side, plus meaning right, but that should make sense. Plus is on the right and minus is on the left. So that plus is just kind of a placeholder, meaning on the right side of 1. So if we're traveling and getting close to x on the right side, what is the y value that I would need to use to fill in a hole so that this would be continuous? I don't have to lift my pencil up on the interval from 1 going to the right. And that value is 3. Basically, if there's a hole there, you fill it in. So it's just filling in on one side. So the limit as x approaches 1 on the right side of f of x is equal to 3. Okay, now let's take a look what it would be. Let's go back to the original function. It looks like this. And this statement still holds true because this is the value we need, the y value that we need to fill in that hole right there. So it's continuous on the right. Now, what about on the left? It's already continuous on the left up to that point, and so the value that it is the value that needs to fill in any hole if there were a hole. So that is the value of the limit. So the limit as x approaches 1 from the left side, we use a little minus to mean on the left, of f of x, then would be equal to 5. So we have a left-hand limit, or right-hand limit that is, and a left-hand limit, 3 and 5. Notice that these two limits are not the same. Now, if the two limits are not the same, that means that the limit as x approaches 1 of the function itself, so x approaching 1, that means from any side, from this side and this side. So is there any value, y value, that I can use to change what that is? Like this one or that one or any other one at all, so that this function isn't jumpy right there, so it actually is continuous from here to here? And the answer is no. There is no y value that will. And the point is, if these two limits are not equal, even if they do exist, then there is no possible way of just choosing one single y value to make this function continuous on an open interval or any kind of interval that contains 1 on both sides. So here we're looking at, if we don't put a plus or minus, we're looking at both sides, and we need a whole interval containing this, going this way a little bit and that way a little bit, to actually be continuous as we draw. And it's impossible if these two things are different. Hence, we say that the limit as x approaches 1 of f of x just does not exist. So maybe we could write D and E for does not exist if this case happens. This happens with a jump, but the right-hand limit and the left-hand limit actually do exist. Thanks for watching.